Hi class, my name is Daniel Uribe. I'll be your instructor for CS 3305, section 5. Um, so, uh, I know this is the first video that I've posted for this class, but this is actually the third time I've done this today. There's been various other complications as I adapt to this format. So, I got a little bit of experience at the end of last semester in the spring, with all of this going around. And so I have a little bit of practice. Hopefully, this won't provide a terrible experience for you. The webcam is new for me, so you'll still get at least a little more engagement than I was able to provide last semester, which I would consider a boost. So this lecture will be pretty quick, pretty short, because I have run over on my time, and I need to make sure that I get this out to you. But for those of you that are looking to get a jump on your reading, we're going to be using the 8th edition of Rosen, Discrete Mathematics and its Applications. And in the course, the material that you'll get homeworks over and that the exams will cover will be chapters 5, 7, 8, 9, 10, and 11. And so for those of you coming from 2305 in my class, we did cover induction and recursion, and I know that typically is something that's covered in pre-calculus as well, but I also know that it can be a tricky subject for undergrads, and I wanted to make sure that everyone in the class felt comfortable with it, so I went ahead and included it in the material. And then chapter 7 will cover discrete probability. And so I could never talk about probability and statistics without bringing up its origin story. And so I will get more details on that, and whenever we talk about chapter 7, I'll make sure to include it, but it's one that always amuses me. Advanced counting. So this will have to do with algorithmic runtimes, and I know that's probably this vague subject or whatever to discuss right now. But whenever you start to deal with a user base that gets really large, or just a really large data set, for those of you that end up doing things in the area of scientific computing, the advanced counting methods of determining your runtime complexity, they start to become really important. So whenever a program only has one user, it's not terribly important that it's well written. You can really get away with loops inside of loops inside of loops, and it still won't matter, right? Because a billion computations for your processor on a modern processor will take less than a second. So in general, who cares, right? But whenever you get up to 10 or sometimes even 100, if it's really poorly written, then you can start to feel a bit of a strain. And for 1,000, even if it's well written, if they're using it simultaneously, then that can really strain your resources. And then for larger companies like Amazon and Google and Facebook, where they're getting millions of users using it simultaneously, and their user base is like in the order of a billion, then it really starts to matter in terms of performance what it is that you've written, what code is being executed over and over again, and not just before you can optimize the code, you need to understand where it is that there's room for improvement, and so we need to learn how to count that, how to gain this understanding of, well, how costly is this statement that I want to execute. And so we'll go over that a bit in chapter 8. Relations as opposed to functions, right? And so this is really the theory that lays the groundwork for understanding databases and data sets. So I know not every one of you will take a course in databases while you're at UTD. I know that I didn't, but it didn't take very long before I entered the professional workforce before I began dealing with them, and then I ended up spending a fair bit of time. And if it's done right, as you're developing a proof of concept or whatever, then you're not constantly meddling with it, but you still need enough familiarity so that you can normalize it properly and expect reasonable performance. And then you'll hand it off to a database administrator, or some of you may even become the DBA, and they'll perform additional tunings, and they'll make suggestions about moving certain procedures from the code base into like a stored procedure, and then they'll make other optimizations regarding indices and when to re-index the database and perform certain maintenance tasks on it. When to, there's times whenever you have to basically clobber the old history or whatever because you can't shrink the log file, and there's a million minutia or whatever, and it's nice to have someone else to deal with that. But in working with them, they will really appreciate if you have at least a basic understanding of how data relates to one another. And so our familiarity with relations really comes from functions, the maps that we graph, where f of x equals some operation on x. And so you're given some value x, and then you get spit out some value y, and that pair becomes a relation. It becomes an ordered pair. And so that's what we're familiar with, and the goal, whenever we go over this subject, is to translate what we're already familiar with to, as developers, as software engineers and computer scientists, into what we will be using, the more abstract concepts around that. And so that'll be what we go over in Chapter 9. Graphs. The example I like to use is just consider the interstate highway system here in America. And so in this analogy, the highways would represent the edges of the graph, and the cities that the highways run through would be the vertices. And so you can really access any, you can get to any city that's on the system by multiple routes. So if you consider going from Seattle to Miami, then you can imagine going across the north and then going down the east coast, or going down the west coast and then going across the south. And either way gets you there just as fine, but you'd want to consider the comfort of your travel, and whether or not your path would take you through some other cities that you would like to visit, whether it's summer or winter. So if it's winter, you're probably going to want to avoid the north, and if it's summer, then you may not want to drive through the desert in the summer. So there's these other considerations, these other costs that would factor in as you compute your route. And so this is just a very abstract discussion about graphs, but the problem is very similar in the computer science world as well, where you need to understand how to get from A to B, and you want to be able to tell a computer how to do it, but how do you tell the computer how to do it for all cases? Like what rules can you provide it with that'll allow it to solve it in an efficient manner? And that's why we're covering it after advanced counting, because there are very, very many possible routes, and so you can't even consider them all within the life of the universe, basically, or within a billion years, we'll say. So that becomes a problem. So if you don't have a billion years to solve a particular case, then what rules can you provide that will converge to a solution in a reasonable amount of time, or in other cases you might consider heuristics as well. But anyway, so we'll discuss that whenever we get to graphs. And then the last chapter that you'll have homeworks on and that you'll be tested on is chapter 11, which covers trees. and so trees are a data structure, and they're really convenient. And you can think of your file system as being a tree, as following a tree structure. So if you're a Windows user, then your root in this case would be the C drive, and then it would have several children. That would be all of the folders and files that are underneath the C drive, and then each of those might have additional folders and files and so forth. And so the files themselves would be the leaf nodes, and an empty folder could also be considered a leaf node. And so each path in this case is unique, right? So the file path is unique, and you get to it by going from the root to a child to the correct child there and so forth until you've reconstructed the file's path. So that's basically trees. You can add additional restrictions to them, like making it a binary tree, so that each node, each point, or in this example, each folder would only have 2 children and so forth. And that provides you with certain other guarantees that make it a little bit easier to consider the problem. And so we'll discuss that as well. And then I'm hoping that either for the next class or sometime next week to be able to go over some background material that is helpful for everyone to know. I had a course whenever I was doing my undergraduate work that basically reviewed all of operating systems, and it really caught me up because I hadn't taken that course at the time, and so I think that can be helpful in this course as well for some of these concepts, if we can all at least reach some minimum floor of understanding, so we're all at least building from a common groundwork. And so hopefully, like I said, that'll either happen next time or sometime next week. Your first homework won't be until next Tuesday. I've posted the syllabus, and your first exam won't be until sometime in September. So there's 3. Each one of them will be take home. Each of the homeworks will be posted. I'll give you a PDF and a TeX file, which is a file format for LaTeX. And so LaTeX is it's the way of your future. So every homework assignment will come with potential for 50-point bonus if you submit your work in LaTeX, and I'll provide you the questions and already typed up. And I would recommend creating an account with overleaf.com. And so you can create a free account if you have a valid email address, which is UTD students. You should all have a valid email address. But you can also do it with a third-party email. I really don't care which email you use to sign up with it. I never see that. And so you would take the TeX file, you would copy the source into some other you'd create a new project on Overleaf and copy the source in there, and then you would do your work in there. And so yes, it's a little bit more work, but I think it's less than the 50% additional work that there's the opportunity to gain in terms of score on your homework. And so my hope is that with providing this opportunity to you, that you don't really stress about the homeworks. Maybe it relieves a little bit of pressure surrounding the tests as well, and you're able to focus a little more on the material and a little less on your grade. So we'll see. It's gone well the last 2 semesters where I've tried this, but we'll see. And so I do have some notes that I've typed out, and we'll go over them for a little bit. I know I need to post this video so that no one feels lost or forgotten in this class. And we'll spend a bit more time going over the material, or next time on Thursday whenever I post. Okay, so let's jump on over to the notes. And we'll begin by reviewing chapter 2, which dealt with sequences. So I feel like this is a good starting point if you're going to jump into recurrence relations and induction. Sequences are generally there's a formula to them, unless you're discussing like trials in a measurement of probability. But in this case, it's just a sequence of terms derived from some formula. So, for example, the harmonic sequence a sub n equals 1 over n. You can compute any term in that sequence by taking the in, which defines the term in the sequence. If you are using one indexing, which is computer scientists, we won't dull us, but whenever we're in the math realm of discrete math rather than the computer science realm, then we will be one indexing the sequences. Then you take the n and you stick it into the formula, and then it gives you the value of that term in the sequence. So the first term is 1, the second term is 1/2, and the third term is a third. A geometric progression, you start with some number, which is just a constant, and we'll call it a. And then, so if a is 10, then you modify it by multiplying it with r to the n minus 1 in this case. Right? So if this was, or we'll say r to the n. So where our initial term, a0, is just our constant, it's our choice of constant, which we said was 10, then we'd modify it by multiplying it by some term, r, which is our common ratio. So if r was 1/2, then we would have a constant times the geometric sequence, where this would be a times 1/2, and then a times 1/4, and then a times 1/8, and so forth, and a times 1n. Right? But the ratio doesn't have to be less than 1. It can also be 1 or greater. If r is equal to 1, then this entire sequence is just the same number repeated, and so it's typically not considered to be an interesting sequence. But if it's larger, let's say r, okay, so let's say that a is 3, and then r is 10, right? Then this turns out to be just a progression of adding zeros in our decimal representation, so that this is 3, and then 3 times 10 is 30, and then 3 times 10 squared is 300, and then the next term would be 3,000, and so forth. So any sequence of that form where you have some constant and then you multiply it by where each successive term is just taking the power of some other ratio, some value r, and then multiplying it by that initial constant. That is a geometric progression. And one example of that would be the alternating sequence, which I think is a good one. So you start with b0 equal to 1, and then your common term, the ratio, is -1, and then -1 to the 1 would take that initial term and make it -1, and then the second term, b2, would be -1 squared, so you would just get 1 again. The third term, so the third term and all other odd terms would be -1, and all of the even terms would be 1. So it shows that even without choosing r to be 1, you can still get a sequence where it's not moving a whole lot, it's just hopping back and forth between these two numbers. Okay. Another one, so the geometric progression had to do with multiplication. The arithmetic progression has to do with addition. So in this case, you again start with some initial value, and then you add to it by some common difference, and then you add to it by 2 times that common difference, and then 3 times, and then n times that common difference. And so arithmetic progressions you can think of as the precursor to lines to this continuance definition. So if you dealt only with the integers, um, y equals mx plus b, then this would be this would be b, right, and given a line in slope-intercept form, and then this would be m, and then this constant 1, 2, all the way up to n. That would be your x. Right? So if you only chose the x's to be integers, then you would end up with an arithmetic progression. So it's something you're already familiar with, but we've gone back and we've added these definitions to make it a little more confusing and seem a little more foreign. But yeah, you've been dealing with this since like 7th grade. So don't sweat too much about arithmetic progressions or geometric progressions. Okay, so then the next one, strings. Okay. Okay, so this is just another example of an arithmetic progression. And you see it still has that y equals mx plus b format. And then, and then it's just a quick note on strings. And so I know that binary format and really anything other than decimal representations is very likely really foreign to you right now. And there's really no way around becoming comfortable with them other than working with these other formats a little bit. And so we'll go over ways to become really uncomfortable and then get a little more comfortable with it as we go on. And so just keep in mind that we will be jumping back and forth to binary and possibly hex at some point, maybe. Yeah, probably not hex, or yeah. Anyway, but we will be going back and forth with binary and maybe hexadecimal and maybe base 6. We'll see. So a string in this regard, it has a couple of different contexts. So if you've already started programming, then you know that a string is just kind of like an English sentence, basically. It's just a series of characters. And so you can have spaces, you can have white space, you can have inline characters, you can have punctuation, the normal characters, numbers, and so forth. And so basically anything that you can type with a keyboard, in this case we wouldn't consider backspace to be a printable character, right? But anything else could really go into a string, including tabs and pipes and slashes and so forth. So that is one context for a string. And if you're not already familiar with that context, go ahead and take a little bit of time to look it up, because you will be working with strings in your career at some point. So yeah, why not separate it out from all of the other tasks of understanding the programming world and take a minute to understand it now. And then the other context of a string is it's just a number. So in decimal, a decimal string would just be the number. So if you had 123.45, then it's the whole number 123 and 45 100ths, and then there's the period in there, and so that could also be considered a string, right? It's those 5 digits and then the punctuation, the decimal point that's in there, or the radix point if you prefer. And so that is one concept, but more than that, we're really interested in just the whole number part of it, right? So if we only factored on that, then it would be 123. So those 3 digits would make up a string. So you can also, in the way that we deal with decimal, and I'll spend a little more time talking about these expansions for other bases, but you can also have that same string represented in binary, and so let's see, 123 is is 128 minus 5. I'm not going to be able to conveniently come up with the binary representation for this. But it could also be represented in binary, or just another 3-digit or 3-bit word. A 3-bit binary string would be like 101 or 111. And so the string length is just the number of characters that appear in it, right? And so whenever I say that here, then like in this example, if you go over my notes, then that's kind of what I'm talking about. And so there's a special term for the string with no terms, no characters in it, and that is the empty string. So okay, so if I lost you on that, if I lost you on all of that, then don't worry too much about it. We'll go over the important parts of it later. Okay. So now, at last, we've reached the concept of a recurrence relation. And so the recurrence relation, it just means that the term a sub n is determined by considering either the immediately previous term or some other term previously defined in the sequence, and possibly more than one previous term, as the Fibonacci sequence will show us. So for this one, let's see. Okay, so what this is saying here is that for a recurrence relation, we're considering previous terms, but we don't go, by custom, we don't go into negative terms in the sequence. So it never typically goes below A0 or B0 or whatever letter you're using to represent your sequence. But the terms have an origin, and that origin is either 1 or 0. But never -1 and so forth. So we just don't consider those. Although if you ever study complex math, then you may get to experience the negative sequence terms. And so you have these dually infinite sequences, one stretching out negative infinitely and the other going positive infinite. But luckily you're in discrete math right now, and so you're safe from such things. Okay, so a sequence is the solution of a recurrence relation if it satisfies the way that the recurrence relation is defined, basically. So let's look at an example, because that felt like a really weak explanation as we were going over it. Okay, so you kind of see what I mean here, right? So you have a sub n is defined in terms of the previous term in the sequence, n minus 1. And it's just whatever that previous term was plus 3. Okay, so you take some natural number, so some number that's greater than or equal to 1, okay. Yeah, and that'll be your term in the sequence, and so we'll count up to that. And then I told you that we would use a non-negative origin for it. So in this case, we're using A0, so 0 is that very first n. And so in order for this formula to work, if you're going to define it in terms of what was, then there must be a beginning, right? It had to start somewhere. And so you're always in a recurrence relation given some basic parameters, some initial terms that will allow you to stop counting backwards. So once you reach A0, just use this fixed value, and that'll allow you to define any term in the future. Otherwise, without this, then you would just be counting backwards forever, and you would never get your definition. You'd never be able to define your terms. So okay, so then the sequence here, we have A1, which we can compute directly from A0. So we're looking for 1, plug it in here, and you get that this term should be A0. We'll use that A0 add 3, and we figure out that our result is 5. If we want the second term, then we compute it from term A1, which we already showed how to get A1. It relies on A0. And if we wanted the third term, then we would compute it from A2. And so you can already see, well, okay, well, what if I just wanted to start with the fourth term? Then how do I get that quickly, right? I mean, as far as I can tell, I can only compute the fourth term if I know the third term. I can only get the third term if I know the second term. And I can only get the second term if I know the first term. And luckily, I'm able to compute the first term because I happen to have A0 already defined, right? So is there a quicker way? Well, yeah, there is a quicker way, and we'll explore that a little bit later on. But for now, yeah, you have to follow the breadcrumbs. You have to go all the way back to the beginning, and so it's extremely tedious. It's extremely slow, and so recursive functions are typically considered to be a little bit slow for this very reason, because you're computing. It's not fair to say a bunch of unrelated data, because it is related. It just it feels like it could be avoided, right? So let's say you're trying to compute the millionth term in the Fibonacci sequence. If you don't have the closed form formula for it, for computing it, then you have to perform a million previous operations to compute a simple addition. So you're just adding two terms, two values, but because you have to recursively find those two values, it gets really slow. And so, one of the questions that this class hopes to answer just in general is, well, is there a faster way to do that? Well, in that case, yeah, there is, and we'll get to that. But for now, just understand that no, you're not going crazy. This is really slow, and it seems really tedious. That if I want the fourth one, I have to compute the third one, and to get the third one, I have to compute the second one, and so on, right? And that is what a recurrence relation is, and so it's a perfectly valid way of defining a sequence, but it leaves something to be desired as a programmer whenever you want things to typically be a bit faster, whenever you want to save operations whenever you can. Okay, so then our next example, we have a difference of terms. So to get the nth term, we need to know the previous term and then the term before that, and then we compute their difference. So here, okay, so I said on this example, you need some halting term, something that keeps you from going back forever. Well, in this case, because we're looking at two terms, we're looking at the previous two terms, we need two base values. We need two initial terms to our sequence, both B0 and B1. Otherwise, we still wouldn't have enough information to compute even that first computed term in the sequence. So, okay, so the first one that we can possibly compute now that we've been given B0 and B1 is B2, and that's just the difference between B1 and B0, which is straightforward enough. And now we can take that value and we can use it to compute B3, and then now that we have B3, we can use both of our computed values to compute B4, and so forth. And it's still the same problem. Well, if I want the fifth term, then I need to first compute B4, B3, and B2, instead of just performing this very simple, straightforward operation that is presented to me. And so for that reason, recurrence relations can be a little unwieldy. And so as developers, we are also limited to the fact that we're dealing with computers, and there are certain limitations. So any machine that you develop on is going to have a finite amount of memory, and the memory is how the operating system maintains some form of structure of what the program is doing. And so there are real operations that are happening within memory, to maintain. It's called a stack. Basically, the call stack is what it's called. And so each time you call a function, it pauses where it is on the one uh, on the current function, and then it attempts to execute the next function. And so in a recursive function, which draws its name from problems like this, that it calls itself, and so another copy of that function is loaded in, this time with different input parameters, and it gets pushed on top of the stack, and then it'll reach the point. So if you wanted to know B5, then it would halt, and it would call that function, a function that computes something like this with B4. But because the terms aren't provided readily, because it's not one of these initial conditions, it'll halt and it'll compute B3, and B3 isn't quite ready for prime time because it needs to know B2, so it'll halt and it'll make another copy, and so you end up getting this stack that is taking up a lot of memory. And if you get high enough in your sequence so that it's had to halt and push on another copy and so forth, then the amount of memory consumed by each function, it doesn't go away. It sits there waiting for that original execution to complete, but it has to build up this entire stack of executed methods, executed functions, and they're never quite able to return. And if it runs out of that finite amount of memory that the operating system is willing to allow this program to consume, then you get what's called a stack overflow exception. And so perhaps a little later in the semester, maybe even next time, I'll show you an example of that and how easy it is for that to occur. It can really happen pretty quickly. It's not a difficult thing whenever you're dealing with recursive functions. And so these are among the types of problems that we have to deal with, and this is a pretty simple example. So this one, like the Fibonacci sequence, deals with two previous terms in the same sequence, but it's another example of a recurrence relation. Okay, and so the initial conditions, which I showed you before, are just the values that are given to you, and you will typically need as many initial conditions as you reach back in your recurrence relation. So in this case, we reach back two terms, but the number of initial conditions isn't limited to the number of terms that are included within the arithmetic. For example, if Bn was equal to B, 2 plus the n minus 7th term, well, we're only using one previous term in the computation, but it reaches back 7 terms. So you would actually need 7 initial conditions in that case in order for it to be well defined. So that's a bit of sleight of hand that may show up on your exam. So don't pay attention to the number of terms. Pay attention to how far back that is reaching, and then that'll tell you how many initial conditions you need to be given in order to actually properly consider the problem. Okay, so then the Fibonacci sequence, which if you've ever dealt with recurrence before, then you've dealt with this, or if you were ever given a pair of, if you were ever given your own island and a pair of breeding rabbits, then you would also be familiar with this function. And so that is, as lore has it, the origin story of the function. There was a mathematician who was trying to count the growth of population of rabbits on a particular island, and he found that it took 2 months for a newborn rabbit to become breeding age, and so that is what this n-2 represents. And so it's the number of breeding rabbits from 2 months prior, plus the number of all rabbits from the previous month, and then that will tell you how many rabbits you can expect to be breeding or to be alive at this point, right? And so it's a really cool observation that he made. And yeah, anyway. So that's where the problem comes from. But it appears, in other contexts as well. And so the sequence itself begins with two initial terms, and so instead of using 0 and 1, in this case we've used 1 and 2, and then you just plug in the numbers. So to get the third term, to get F3, you would plug in 1 here and 1 here, and you see that the third term oh, I'm sorry, there is a typo here. This should be 0 and 1, and then 2 would be 0 plus 1. No, I'm sorry. And then 2 would be 1 plus 1, which would be 2. And then 1 plus 2 would be 3, and so forth. 2 plus 3 would be 5, and so on. Right. So I will make sure to get that fixed. Anyway, I don't want to confuse you in that regard. But yeah, so that's the Fibonacci sequence. And then throughout the notes, you'll see that there are some examples posted. So the last time I taught this class, I asked my students what languages they were most familiar with, and I got a smattering of answers. So some students were familiar with C, some with C++, some with Java, some with JavaScript. And I can write in any of them. You'll see examples from various of them. But really, given when you are entering the field, I personally feel that in order to find work, it's probably to your benefit to learn JavaScript, since front-end development it gives a great first impression because you're able to show non-developers, non-programmers, an interactive application pretty quickly. I think it is important to understand, C. I think especially if you want to understand operating systems and kind of the theme of this course, what it is that a program can tolerate and still perform well in terms of the code that you're giving it to execute. I think C is really important, but I prefer to give my examples in JavaScript just to try and familiarize each of you with that, since I feel like in terms of finding work there is good opportunities with JavaScript. But the language that I was most familiar with throughout my career was C#. And so most of the work that I've had has been exclusively in C# or with an API that was written in C# and then a JavaScript front end with HTML, obviously HTML and CSS. So there's a lot of ground to cover, I think, before any of you can really consider yourselves as having mastered the subject. But I will do my best to provide examples in languages that you're familiar with, so C and Java, and I'll try to expose you to C# or but a fair number of the examples that I'll use will also come in JavaScript, and that's just because it's really easy to find something that will interpret JavaScript, right? Like if you have a Chrome browser, or Firefox, I believe, offers a console, and I think even Microsoft Edge as well, then you have an interpreter right here. So let A equal 5, let B equal 10, A plus B, right? And as simple as that, you're programming, or you're writing executable code, and so for that reason, the examples will tend to be in JavaScript, especially whenever they're ad hoc. But anyway, if you have another language and you feel really uncomfortable with anything else, then feel free to send me an email, and I'll try and make sure to include an example in that. And hopefully having that familiar example, you will then take the initiative to also try to at least read what's happening with the program in one of these other languages where the example is provided. So this example is in C, and then this example is in Java. And in both cases, it is the recursive form of it rather than using a loop. And so I've provided the opportunity for a Stack Overflow exception just once you get far enough into it. And for the keen observer, you'll see that we're not actually caching any results here either. So we're retreading some of the same ground. So if we pass in 10, like we want the 10th term in the sequence, then we will recursively execute steps for the terms 9 through 1 over here, and then we'll recompute values 8 through 1 over here. And so it's a bit wasteful, but I wanted to leave that in to explain that. And so we could do some stuff here. I think it would be easier to get rid of that using a loop rather than reworking this function. I believe anything that is recursively defined with a function can be replaced with a loop given enough effort. And so I think once you've experienced enough Stack Overflow exceptions, then you will probably want to put in that work whenever you're developing solutions to problems of this form. But anyway, I just wanted to take a moment to point that out. So again, here's the Java version, and then here's the definition of closed formula or closed form solution. And so rather than having to compute it over and over again, the idea is that for most of these problems, or at least a healthy number of them, you can replace that recursive definition where you're recomputing, retreading the same ground with something that'll just spit out the answer. Okay, and so that concludes Chapter 2's review. And next time we'll go over Chapter 5, Induction and Recursion, unless we use that time to go over the basic groundwork for an overview of computer science. So okay, stay healthy everyone, and I will see you all on Thursday.